This is nature at her worst. Shredding buildings, drowning cities, killing thousands.
The hurricane is the most deadly and powerful system or phenomenon you're going to find on this planet.
They're the largest storms on Earth. How they gain such power is a puzzle with missing pieces. Scientists follow the life cycle of these killer storms, from birth to death, to solve the mystery. They are one step closer to parting the clouds, to reveal the anatomy of a hurricane. Hurricanes, nature's fury. A single strike can cost billions. Every year, hurricanes claim lives around the world, and they're becoming more powerful.
You have this whole devil's brew of things going on in a hurricane. Incredibly high wind, waves crashing on shore, intense thunderstorms. It's just an incredibly scary blend of things happening all at once.
Scientists struggle to predict where a hurricane will strike and how powerful it will become. Only by studying it from cradle to grave can scientists learn how it functions and perhaps forecast where and when it will hit. This is the story of science against nature at its most furious. Lives depend on the outcome. Over 80 hurricanes form each year around the world. Of those that form in the Atlantic, roughly 1/3 will strike America. The names are familiar: Andrew, Wilma, and Katrina. The future will bring new tragedies. And the race is on to understand how hurricanes work. Chris Lancy from the National Hurricane Center is trying to crack the hurricane code.
One of the primary goals of the Hurricane Research Division right now is to better understand the life cycle of hurricanes at their infancy, at their beginnings, the genesis, and to maturity, and then to the decay.
Ignition.
The search for answers starts thousands of miles above the Earth. Satellites allow researchers to spy on a weather system born far out of sight of land. Images taken 22,000 miles above Earth reveal the genesis of the storm. 85% of major Atlantic hurricanes actually start in one of the hottest, driest places on Earth: Africa. In summer, the vast Sahara heats the air above it. As the air warms, it rises, climbing over 2 miles. The warm air pushes the existing weather patterns higher, forming an atmospheric disturbance. Scientists call this the African Easterly Wave. It travels west across Africa at about 500 miles a day. Converging winds on the east side of the wave trigger the development of thunderstorms, the seeds of our hurricane. Over the warm waters of the Atlantic, the thunder cells grow and merge. Atmospheric pressure within the weather system drops. Winds rush in to fill the gap and grow in strength. When they reach 23 miles per hour, meteorologists call it a tropical depression. Computers at the National Hurricane Center track every growing storm. Getting information as early as possible is crucial.
If we can't forecast, the genesis or beginning, we're going to be behind the curve in forecasting the rest of the formation of the storm itself.
Satellite data is vital, but it's not enough. They need to see inside the storm. That's the job of Jim McFadden, hurricane hunter.
You have to know what's going on in the storm full time. And the only way to get the information like the highest wind speeds, the lowest pressure in the center of the storm, is to actually put a plane into it.
The Hurricane Hunter's workhorse is the Lockheed WP-3D Orion turboprop aircraft, packed with scientific instruments and radars. They load data-collecting probes and fly out to meet fledgling hurricanes 5,000 feet above the waters of the Atlantic Ocean. The thunderstorms within the depression group together. Atmospheric pressure keeps dropping, causing wind speeds to increase. When they hit 39 miles per hour, the depression gets reclassified. It's now a tropical storm. The storm pulls in air over such vast distances, the airstreams actually curve. Greg Holland explains how the thunderclouds begin to spin.
It steals some of the rotation from the Earth system to actually give it that turning. It's an effect we call a Coriolis force.
The direction of the storm's spin depends on whether it forms in the top half of the Earth or the bottom. In the northern hemisphere, the Coriolis effect pulls winds to the right and makes the storm spin counterclockwise. In the southern hemisphere, the wind is pulled to the left, which makes the storm rotate clockwise.
If there was no Coriolis, the hurricanes probably wouldn't spin up because the low pressures would be filled and that would be the end of the storm.
Rotation alone can't turn a tropical storm into a hurricane. Up to 28 tropical storms form each year in the Atlantic. On average, only 6 become hurricanes.
You have to have a few kind of key ingredients. You could almost say it's like a hurricane recipe for things to begin. One of which is you need a bit of spin to get things going. Another key ingredient is you need thunderstorm activity. Hurricanes are fueled by the thunderstorms. And the third key ingredient is you need a warm ocean. You need waters at least 80 degrees Fahrenheit for enough energy to be available for those thunderstorms.
The warm waters of the Atlantic Ocean act as fuel for the growing storm.
It's sort of like you go down to the tank and fill up your car. You put a certain amount of energy, if you like, into the car, and then you can drive at a certain distance.
As the surface water temperature of the tropical Atlantic rises, trillions of energy-bearing water vapor molecules evaporate into the atmosphere. They rise higher, they cool, and condense into clouds. This process releases heat, which warms the air around it, pushing the clouds even higher. Now the storm towers 10 miles high. The air within is no longer warmer than the surrounding atmosphere, so it stops rising. The system flattens out to form an anvil cloud. There's still one thing that could stop the storm from becoming a hurricane. High-speed, high-altitude winds. These can shear off the top of the storm, destroying its structure and the flow of energy within it.
You need what's called a minimum of wind shear. And wind shear is just the changing winds with height, the difference between just above the ocean and about 8 miles up. If that wind difference is about 20 miles per hour or greater, hurricanes don't form.
In the growing tropical storm, the wind shear is low and it continues to gain strength. As the winds hit 74 miles per hour, it gets a new name. This is now a hurricane. It has the potential to become the most destructive weather system on the planet. The hurricane is 200 miles across and heading straight for land.
Whether you're flying into it by aircraft or watching from space from our satellites, then it's approaching its most beautiful stage. So people like seeing them to some degree, but we also realize the horrible problems that hurricanes can cause.
McFadden's Hurricane Hunter team have to fly into these killer storms. With data from the eye of a hurricane, scientists can estimate how powerful the storm might become. The center of the storm is still hundreds of miles away when the hurricane hunters hit the first rain bands. These are fierce clusters of thunderstorms that spiral out from the center. They form as water vapor evaporating from the ocean rises into rain-bearing clouds.
We usually pick our way through the rain band so that we avoid most of the severe turbulence in a rain band, and then on towards the eye wall.
The eye wall is a dense wall of cloud around the hurricane's eye. It's where the weather is most extreme. Here, winds can reach 200 miles per hour. The rain is torrential.
It's where a lot of the upward transport of moisture, the conversion into clouds, and the heating occurs to get the cyclone going. So this, if you like, is the pistons of the heat engine of the hurricane.
The hurricane hunters make it through the eye wall. Inside, a circle of calm weather up to 40 miles across. The eye is the heart of the storm, the pivot the hurricane rotates around. At the center of the eye, the air is relatively still. No rain, blue skies.
When we fly into hurricanes, you don't see much, and you're going through the eye wall. It gets very dark, and then all of a sudden, the plane goes smooth, and we're in the eye, the calm part. And you're blinded for a second because the sunlight is so intense, and your eyes finally get used to what's going on. You look around, and you're in this, it kind of looks like a gigantic bowl. It's like a 40-mile wide football stadium. Just what a hurricane looks like.
McFadden's mission is to drop a probe into the heart of the storm.
This is one of our GPS drop-ons, and it's proved to be probably one of the most important tools for collecting data in hurricanes that we've had over the last 10 years.
The probe parachutes down through the eye and measures the hurricane's temperature and humidity twice a second. Built-in GPS gives data on wind speeds and direction. But the most important reading is atmospheric pressure. As the hurricane grows, the pressure at its center drops. The area of low pressure sucks in more warm, moist air. If the hurricane hunters can get a pressure reading from the eye, meteorologists can estimate how powerful the storm may become and how long it may last. They also monitor the size and shape of the eye. As the storm gathers strength, the eye can contract, making the winds even stronger. In 2005, Hurricane Wilma did just that.
What this is a loop of the satellite imagery. And so this gives you a sense of the evolution of the whole life cycle of Hurricane Wilma. And you'll see the development of the eye, very tiny eye. When you get a pinhole eye, a very tiny eye, that's often indicative of a very small inner core. And in general, as the eye and eye wall gets smaller, you tend to have faster winds, stronger winds. It's analogous to an ice skater. As she brings her arms in and she's rotating, she spins faster.
Scientists classify the hurricane's strength according to its highest sustained wind speed, taken over a 1-minute period at 33 feet. Category 1, wind speed 74 to 95 miles per hour. Category 2, wind speed 96 to 110 miles per hour. Structural damage to roofs. Category 3, up to 130 miles per hour. Many buildings irreparable. Category 4, winds up to 155 miles per hour. It smashes solid walls. Category 5, the deadliest. Large-scale destruction and widespread flooding. Little can survive a Category 5 hurricane. In the Atlantic, the approaching hurricane is still a Category 1. Ahead lie 2,000 miles of warm water, fuel for a thirsty storm. The battle now is to predict how powerful it will become and where it will strike. A killer hurricane stalks the Atlantic. 8 days ago, it was just a cluster of thunderclouds off Africa. Now, it's a Category 2, over 200 miles across, winds near 100 miles per hour, and rising. In less than 48 hours, it will hit America. But where?
Nowhere is safe on the Gulf Coast or the East Coast of the United States. And the more we can understand of the dynamics of these storms, the more we can understand what exacerbates the impacts, the better it is for everybody.
It's vital for meteorologists to understand why hurricanes take a particular path. If they can better predict where these killer storms will hit land, they can broadcast more accurate warnings and save lives.
Now, how a hurricane moves is due to a number of different factors, of which there are two main ones. The first is that it acts just like a cork in a stream. It is actually blown along by the large-scale atmospheric winds in which it's embedded. Then the other major component is that they actually use up a little bit of the Earth's rotational effect to allow themselves to push themselves along.
To predict where the hurricane will strike, meteorologists need information about the weather systems that surround it. The trade winds, a prevailing pattern of winds found in the tropics near the Earth's equator, push the hurricane west at speeds of up to 20 miles per hour. But before the storm makes landfall, it must negotiate a region of high pressure off America, known as the Bermuda High. This high-pressure dome moves across the Atlantic and creates winds that spin clockwise. Depending on its size and position, it can steer a hurricane harmlessly into the Atlantic or straight into land.
It's the changes in the wind flow that are important. Whilstsoever the wind is in one direction, it's great for forecasting because it makes it really easy. It's when they're at that change state that it becomes very, very difficult.
Meteorologists have recorded the paths, frequency, and intensity of Atlantic hurricanes. Where and how a hurricane strikes can appear random. Scientists use computer models to try to establish patterns to better predict where and how powerfully it will hit land. Joe Sion works to improve the data that inputs into these models.
What models are doing are trying to, as closely as they can, simulate exactly what Mother Nature is doing. And once we get to the point where we say, you know, we have done that, we have improved the model's representation of nature, what will result is improved forecasts going forward.
Over the last 20 years, computer models have made huge advances. Faster, more powerful processors, better weather data, and greater knowledge of hurricane anatomy allow meteorologists to make better forecasts. Robert Rogers and his team at the Hurricane Research Division play a key part in piecing together this puzzle.
The track forecasts have improved significantly, but our intensity forecasts have essentially remained constant. They have not improved or improved very little over that time. So we have our work cut out for us, and that's really what we're focusing on now.
Scientists now have a much clearer idea of where a hurricane will strike. Estimating how powerful it will become is tougher. The hurricane tracks 500 miles south of Bermuda. It's now just 36 hours from landfall. It's already a powerful storm. If it hits an ocean current or eddy where the water is even warmer, it could rapidly intensify. The warmer the water, the more powerful the storm.
And it's sort of like you put a bit of turbocharge into your car. Suddenly it's got more fuel, suddenly it can actually start accelerating its intensity, and away it goes.
It's what meteorologists fear most, a storm that gets a kick of energy.
From a forecasting standpoint, that's kind of the nightmare scenario. So whereas, people went to bed one night expecting maybe a Cat 1 to make landfall, they might wake up the next morning and looking at a Category 3 or Category 4.
Scientists don't know why some hurricanes rev up and others don't. The answer may lie in a part of the hurricane called the boundary layer. It's the region at sea level where the hurricane draws its energy, where sea and air interact.
So if we want to really get a good handle on intensity change, we have to understand how the energy is transferred out of the ocean.
Sion is part of a team trying to unravel what happens at the boundary layer. To bring back the data, scientists must skim over waves up to 3 stories high and fly straight into one of the most dangerous places on Earth. The hurricane is 36 hours from hitting America. Winds near its eye blow 115 miles per hour. It's 300 miles wide and still growing. Question is, will it get a jolt of power? Some scientists believe the answer lies in the boundary layer. It's here the storm draws heat from the sea as fuel. Scientists need to refine their understanding of the exchange of energy that happens here and how wind speed, friction, humidity, and air and sea temperature affect how the hurricane intensifies. Until recently, scientists lacked reliable data from the boundary layer. September 2003. As part of an experiment called Sea Blast, hurricane hunter planes flew straight into the deadly boundary zone of Hurricane Isabel.
Sea Blast itself was to look at the dynamics of the boundary layer in a hurricane. We were willing to fly down to 200 feet as long as we can maintain visual contact with the surface.
Below, a churning mass of 40-foot waves. Around them, wind eddies that could swat them out of the sky.
When you're flying that low, you can see every single wave. And some of these 30 or 40-foot waves look visually like they're about to touch the plane.
They flew so low, sea spray drenched the plane.
We noticed that the windshield was turning white while we were flying at 200 feet in a hurricane. We didn't realize, though, that all that salt was coating the engines.
One of the engines had a problem, and we had to secure it, turn it off.
They regained power just in time and limped back to base. Their data gave scientists fresh insight into how wind speed affects the amount of energy entering the storm. As a result, new data was fed into computer models. Data from the boundary layer will improve the accuracy of forecasts. But data from these missions isn't enough. And Operation Sea Blast proved flying through the boundary layer is too risky. How to get more data without risking lives? Don't send people, send a probe.
What you're looking at here is the Mark III aircraft. It's an Aerosonde Corporation aircraft. That we think that this is a very compact aircraft that can do a lot of things and measures what we needed to measure.
Sion's team loaded the Aerosonde with instruments to measure meteorological conditions within storms. It headed toward the hurricane's strongest winds, piloted via satellite.
Only 100 miles since our turn.
In 2005, they flew into Tropical Storm Ophelia.
We rode it up and down, and the aircraft survived that. And this is the first time we've really been able to look at data like this.
The Aerosonde can fly into the deadliest parts of the hurricane and stay there up to 12 hours.
The only thing I can compare it to is what I saw on TV with these Mission to Mars, where the group of scientists send something out and you see them cheering when it finally gets on the surface of Mars. You just feel just a great sense of accomplishment. And for me, it goes beyond that too, because I know what we're doing is really, we're trying to help people. We're trying to save lives.
Scientists hope that in the future, aerosondes will regularly fly into the hurricane's boundary layer and send back constant data. This will improve their understanding of how storms intensify and help them spot the warning signs. The better the forecasts, the more lives saved. 24 hours from landfall, the hurricane has strengthened to Category 5, a 350-mile-wide heat engine. It converts the warmth of the sea into winds over 155 miles per hour. Inside the storm, rising water vapor and churning seas mean the hurricane picks up 2 billion tons of seawater every 24 hours. The rains inside the storm are torrential. The path is set. Hurricane historian Jay Barnes knows what happens next.
Here we have a hurricane about to strike land. We know what is going to happen because we've seen it happen before. A powerful storm, very, very large in diameter, going to affect hundreds of miles of coastline.
A hurricane's biggest killer is water. Not rain, but a wall of water called a storm surge. 90% of all hurricane deaths are from drowning. Oceanographer Stephen Begg watches the Atlantic for the first signs of the surge.
Storm surge is not something that's been seen by very many people, and even fewer survivors, so that it's hard to describe to people.
Forecasters monitor the hurricane closely. From the wind, Ivar Van Heerden picks up clues about the size of the surge.
The stronger the winds, the more water you blow towards the shore, the more surge you're going to see.
As the first part of the eye wall hits the coast, winds accelerate. The surge reaches its peak.
The surge intensifies as the eye gets close because the strongest winds are around the eye. So you then, under the influence of the stronger winds blowing the water landwards, piling it up on top of what's already been piled there, and that's when you get the intensification.
The highest winds blow on the right side of the storm. If the right side strikes first, the surge will be worse. That's because the hurricane is not only spinning counterclockwise, but is being driven by winds across the sea. On one side, spin adds to forward motion. On the other, it subtracts. A storm spinning 90 miles per hour and moving forward at 10 will have winds of 100 on the right side and 80 on the left. The higher the winds, the higher the surge. August 2005. A Category 1 hurricane struck Florida, then transformed into a 400-mile-wide killer in the Gulf of Mexico. It was set to strike the Gulf Coast, right-hand side first. The hurricane's name, Katrina. Professor Van Heerden watches the path that Katrina is taking.
We started to suspect that Katrina potentially could hit New Orleans even before it made landfall in Florida. And the reason being the weather patterns were such. The Bermuda High had moved a little bit to the west, that the wind currents would be bringing anything that entered the Gulf of Mexico into Louisiana. The curvature was there. And of course that proved true.
At 6:10 a.m. on the 29th of August, Hurricane Katrina hit the coasts of Louisiana and Mississippi. In the midst of the carnage is storm photographer Mike Tice.
The storm surge was coming up to Highway 90, and by 8 o'clock, it was already coming to the front steps of the hotel. When the storm surge started to get around 12 to 15 feet, it made it into the first floor of the hotel, and a car comes floating through the hotel lobby. I saw it coming ahead of time in the parking lot. it perfectly came in, so it came directly through the front glass doors, crashed into them, and the horn started honking, the lights started flashing. It was echoing inside this lobby. Of course, all the power's out. It's pitch dark in there. And it is one of the most horrifying, scary things I've ever seen in my life. It was straight out of a scary movie, and I don't think I could ever have imagined I would ever witness something like that in my life.
The highest storm surge ever seen in America sweeps across the entire region.
This rise of sea level in some areas estimated over 27 feet. And if you can imagine the beachfront like we're standing here today, a 27-foot elevation of the surface of the ocean, with waves, battering waves on top of that, it's quite destructive. And that's what caused the tremendous destruction we saw along the Mississippi coast.
The surge built along the Mississippi Delta. In New Orleans, the levees burst. A city drowned.
We knew that we were going to be dealing with very high death rate. 10 years of research, looking at lots of other floods all over the world, just cannot prepare you to see miles after miles of subdivision and only the roofs are visible. And of course, on the roofs, people frantically waving for help.
Over 1,500 people died. A tragic testament to the power of storm surge. Now it's the turn of the hurricane's eye to hit land. The storm passes over its own havoc. For 1 hour, the rain stops. Clear skies and sunshine break through. What was destroyed in just hours will take years to rebuild. And still, we have seen only part of the hurricane's deadly arsenal. More damage is coming. The hurricane is only half over. Its other lethal weapon returns for a second attack. Wind. "10 days ago, this storm was a cluster of thunderclouds off Africa. Now it's a hurricane at the height of its destructive powers. The storm surge caused terrible devastation. Winds cause even more. As the eye passes over, the other side of its wall hits, and the winds switch direction. At first, this helps. Floodwaters are pushed back out to sea as quickly as they came.
As soon as the eye goes by, the winds start blowing from the opposite direction and starts blowing the water offshore, so that you get the very rapid set down.
As the deluge of water drains away, the hurricane begins to move further inland. Its strongest winds, over 155 miles per hour. The eye wall.
The winds are toppling power lines and knocking down trees, blowing the roofs off of homes and smashing windows. It really is a scene of chaos as the most powerful part of the storm strikes the coast. That's when you see the greatest intensity of impact.
Low pressure pulls air in toward the center of the storm as wind. The closer to the eye, the faster the winds. Some of the inrushing air gets pulled into strong updrafts, and centrifugal force generated by the hurricane's spin pushes some air away from the eye. Most rams into the eye wall, creating a spinning tube of wind and cloud. Bob Henson studies the architecture of this force.
So in a mature hurricane, you've got this complex dance, and it's a very symmetric and beautiful thing, actually.
This delicate balance of forces shapes the speed and direction of the hurricane's internal wind.
So what you really have in a hurricane is wind parcels rotating around the center of the hurricane, like the nickel is here, but spinning faster and faster as it nears the center and tries to rise up, and then finally does rise through the very center of the hurricane, as we're seeing right here. That's what actually happens in a hurricane.
A hurricane's strongest winds are just above the ocean and close to the eye wall. Away from the center, winds slowly weaken. Yet even 60 miles from the core, it gusts well over 100 miles per hour. The damage can be colossal. At the University of Florida, scientists are working with engineers to design hurricane-proof homes. The first challenge for forest masters is to test buildings under realistic hurricane conditions.
So we're trying to understand, how does the whole building perform, in concert to resist these extreme loads.
To test how a building will perform, Masters measures hurricanes at work. His team deploys hurricane-proof towers, loaded with equipment, to measure the winds 33 feet up.
It's incredibly dangerous deploying this kind of instrumentation in the path of a landfalling hurricane. We don't have a lot of time. We wait to the last possible minute to be certain that we know where the storm is going to go.
The data lets Masters map the wind itself. His results confirm the winds change radically once the storm moves off the ocean and hits land. Buildings and even the ground itself cause friction and reduce average wind speed. But as winds are forced over obstacles, gusts become more intense. These turbulent blasts of air can turn a home into matchsticks in minutes. Masters feeds data from the towers into a hurricane simulator. He aims to recreate a Category 3 storm to test how a window performs. This machine really blows. 8 5-foot-tall industrial fans, powered by 4 vast engines, produce the winds. A 5,000-gallon water tank cools this vast machine and provides the rain.
We're taking that turbulence data and we're trying to replicate that at sufficient scale to immerse a low-rise building. And that allows us to look at the performance of all the different parts of the building, such as the windows, doors, and roof cover systems.
The simulator mimics the gusts and driving rain of a typical hurricane. If the hurricane can get inside doors and windows, the difference in pressure can tear the house down. This window is being hit by Category 3 force winds. So far, it's impervious. Piece by piece, the team tests windows, tiles, studying the ways in which hurricanes expose flaws in design and assembly.
Ultimately, if we can make better buildings, stronger buildings, perhaps we can modify our evacuation policies so that people can stay in their homes longer, or, in a higher and more intense events.
As the hurricane travels inland, the value of this type of research is obvious. Buildings with any weakness are ripped to shreds.
My house has just launched a whole bunch of missiles into the air, which is going to damage your house. Your house is going to launch a bunch more missiles into the air, which is going to damage the next house down. And suddenly we have this mass of flying debris that is doing an enormous amount of damage.
The storm moves 15 miles inland every hour. The further it moves away from the ocean, the weaker it gets. Winds drop by half every 7 hours. The hurricane is dying, but it's not dead yet. The hurricane hits land as a full-blown Category 5 storm, a blast of destructive energy. It creates vast floods and devastates coastal towns and cities. But as it leaves the ocean behind, it loses power. A hurricane needs fuel.
When a strong hurricane makes landfall, you see some changes to the characteristics. The structure starts breaking down.
Really, over just a few hours, the death warrant has been written.
The energy source was heat from the warm ocean. Dry land lacks the fuel to keep it going, and the storm's heat engine stalls. the hurricane releases more energy than it gains. Its internal structure, the inflow and outflow of air, disintegrates.
If you're going to write an autopsy of a hurricane that makes land, it probably would say death by lack of warm water, because once the hurricane has moved off the ocean, it's lost that source of heat that sustains it.
Near ground level, the inflowing and outflowing wind meets friction from land, trees, and buildings. The low-level winds die. With no energy coming in, the storm's air circulation falters.
In addition, the winds start to feel the trees and the houses, which impact a lot of friction, and it slowly but surely spins down.
It's like a car running full throttle on an ounce of gas. In one day, a Category 4 hurricane can shrink to a mere breeze. If the hurricane hits mountains, it will die even faster. But sometimes, the storm has thrown a lifeline.
Sometimes a hurricane may briefly re-intensify, and this is a process that's rare and not well understood, but if it passes over very moist land or a marshy area or so forth, it may get a little pulse of energy, and if other conditions are favorable, you might get a brief spin of it.
August 24th, 1992 at 5:30 a.m. Andrew slammed into Florida as a Category 5 storm. After landfall, its winds faded. It limped across Florida for 4 hours, passing over the Everglades. Warm, shallow water temporarily nourished the storm and allowed Andrew to make the deep waters in the Gulf of Mexico. Andrew revived and became a Category 4 storm. It pounded Louisiana. It took another 24 hours for Andrew to die, this time for good. The death of a hurricane marks the beginning of its autopsy by the scientists.
We do an evaluation of the storm itself, the whole life cycle, from birth to maturity to decay, and try to summarize that, as well as the impacts on people.
Scientists have improved their track prediction by 50% in the last 20 years. Huge advances are being made in forecasting just how strong a storm will become. But they may have to factor in a new twist. What will be the impact of rising global temperatures?
We've had a lot of Category 5s just within the last few years. So there's been a lot of discussion and a lot of questions about are we seeing an impact from global warming on this hurricane or that hurricane?
Climatologists combed through more than a century of records. They found that average ocean temperatures in the tropics have risen by 1 degree Fahrenheit. Hurricanes get their energy from warm water. Logic suggests stronger hurricanes. In 2008, the United States Climate Change Science Program announced their conclusion. It points to an increase in hurricane intensity or strength.
It is very likely that the oceans have warmed up due to climate change. It is very likely that we will see, and indeed are seeing now, increases in rainfall in hurricanes because of this, and increases in the maximum intensity.
For now, meteorologists concentrate on the present. Their work continues to reveal new aspects of the birth, life, and death of the deadliest weather system on planet Earth.
We've reached the point where our meteorologists are doing a super job of telling us where they are, where they're going, and what to expect. Well, one of the things that we can all expect is that they're going to keep coming.
Science has shown us the anatomy of a killer. We can't prevent them, but we can learn to predict them. With each new piece of the puzzle, science saves more lives. The power of a hurricane is awesome.